Start the video. All right. As promised, last time, we are basically going to go over largely a lot of what we covered with vectors last time, but now we're going to introduce the notion of dual vectors, and these are going to play as important a role as vectors. And once we get through dual vectors, we will actually have all of the machinery in place to introduce the notion of tensors, which is something I know you've all heard of, but you might or might not have worked with them. And yes, we are going to go way above and beyond Pat Cole's definition of tensor, but anyway. Believe it or not, you've worked with dual vectors before, and I'll show you where and when you've worked with dual vectors. But we define dual vectors by three conditions. One is that dual vectors are straight, directed objects, so much like vectors, in space-time. Okay? So what I have in mind here is that just like with vectors, where I tried to argue that a vector cannot be imagined as actually extended through space, rather it has a direction in space, but a vector is defined at each point. And if the vector is only living at a point, and it happens to be living on a curved space, then PJ is going to tell me if this vector is trying to be defined on the surface of a sphere, then what do we need to introduce in order for this vector to even make sense?
Tangent.
The tangent space. And the tangent space can be different at different points on the sphere. Okay? Well, it turns out dual vectors do not live in tangent space. They have to live in something very similar. Rather, they live on what is called the cotangent space. Okay? And the cotangent space is, I mean, if you're drawing it pictorially, it looks just like the tangent space, so nothing weird there. All right. Now, a second part of the definition of a dual vector is that dual vectors, just like vectors, are invariant. That is, given a coordinate system, they can be expressed in terms of changing components and bases. Okay, well, I'll give you the notation for the basis of the dual vectors in a few minutes. Okay, but this is basically going to play out just like we said it, just like it played out for vectors. The vector itself is invariant under coordinate transformations, but you can express the vector in a coordinate system as components times basis vectors. And then when you transform the coordinates, you have to transform both the components and the basis vectors. Well, it's going to play the same for dual vectors, so it's going to play very much like a vector story. 3 is where we get some new meat in the story, no pun intended. Dual vectors eat vectors and scalars. It's eating, it's got to get out something. Okay? So if I take a vector and a dual vector, and I combine them in a certain sense, which I'll play out momentarily, what you end up with is a vector. And this happens linearly, so if omega is a dual vector, then it can eat two vectors, AV plus BW, where A and B are just numerical constants. V is a vector, W is a vector. Omega is going to linearly eat this, and so what that means is that this is going to be A omega eating V plus B omega eating W, and this is a scalar. Okay? This is just the same linearity structure which you usually coordinate with vectors, so don't worry about it. And also, the dual vector story, when I explain to you where you've seen it and used it before, you'll be like, oh, I do all that crap. Okay, I just have to name it. Now, someone should have asked a question, so I'm going to give someone the opportunity to ask a question. Somebody who's actually here. Okay, Ben.
Yeah.
Ben. Vectors are invariant. Dual vectors are invariant. That should lead you all to ask a very interesting question, which is, well, what the hell is a...
I'm not sure.
You want to phone a friend?
Yeah.
What's a scalar? What is, the question is, what's a scalar? I mean, if vectors are invariant and dual vector, I mean, I thought that's how we define scalars. I just said scalar. What is a scalar? Don't we define scalars as things that are invariant? Right? Okay, so let me give you what a scalar is. Scalars are invariant and their coordinate representation is invariant. That is, there's no components and bases in which we have to expand a scalar in order to express it with a given coordinate system. There's none of that. It's just a number. Okay? So it's important to remember where vectors transform is when we break them up into components and their basis vectors, which is associated with a coordinate system that we're choosing. If we change the coordinate system, we have to change both the components and the basis vectors. Scalars do not require any of that. So you can give me a scalar, give me a coordinate system, change the coordinate system, scalar don't change. Okay? All right. Now, for the story of vectors, in case you don't remember, we had this really nice vector ds, which is dx mu, e hat mu, and this played a very critical role in our development of what general vectors do, because we said, oh, these are coordinate differentials. I know how coordinates transform, so I can figure out how these transform. If the combination is invariant, then I can figure out how this needs to transform. But then an arbitrary vector uses the same basis, so if I know how this transforms, I can figure out how this transforms. This transforms the same way that does, therefore I know how all vectors transform. Boom! Unfortunately, we don't have that kind of starting point for dual vectors. Dual vectors are not associated with coordinate differentials, so we're going to need something a little bit trickier to figure out dual vectors, but fortunately, we have condition 3, the great poop story. Okay? So, here we go. Consider condition 3, and what I'm going to do is I'm going to say if I take a basis vector or a basis dual vector, which I will notate by theta hat with an upper index instead of a lower index, and I let it be eaten, or I let it eat, sorry, the basis vector e hat nu. So this is a dual basis vector. This is a basis vector. Then this ends up giving me delta mu nu, which is a scalar. Okay? And for those of you who plus 1 if mu is equal to nu, and it's 0 if mu is not equal to nu. Okay?
I'm sorry, what?
Sorry, say it again?
The last bit.
The last thing?
Yeah.
Which one?
That one.
This one?
Yeah.
So this is equal to 0 if the values of mu and nu are not the same. So in 4 dimensions, mu and nu can take on the values 0, 1, 2, and 3. So I could consider delta 1, 1, or I could consider delta 1, 0. This is 1, this is 0. Make sense? Hey, are you familiar with the Kronecker delta?
No.
Okay, so this is the Kronecker delta symbol. We won't even go into the Dirac delta or anything like that. We'll use this a little bit in this class, but not too often. But basically, this is the story. It's got 2 indices. If the values of those indices, and I'm talking about the numerical values, if the numerical values are the same, then it's 1. And if they're different, then it's 0. And if you want to write this as a matrix, it's just the identity. Okay, because this is the delta 1, 1 component, whereas this one right here is the delta 1, 0 component, et cetera, et cetera. Okay? All right. Now, this is something promising because we know how this transforms. We know how this transforms. So we can use that to figure out how this transforms. In the same way we played it out with vectors. Okay? So here we go. So delta mu is a scalar, and I'm just going to erase this and make some adjustments. So, yeah.
So are we just making a definition for theta hat here? Is that what's going on?
Yes. Yeah. So theta hat is so far just a label. I'm about to find out some information about it. In particular, I'm going to find out how it transforms. Okay? So here we go. Yeah, I guess I should say this. So maybe I'll say it. I don't know where I'll say it. I'll say it here. So a dual vector omega can be written as omega mu times theta hat mu. In the same way that a vector can be written in terms of its components times e hat mu. Okay? And this whole up and down business will make sense in a few minutes. But just remember, anytime you have a repeated index, it should come in an upper-lower pair. Okay. All right, so let's exploit the invariance of this. So we can imagine if we transform theta, it goes to theta mu prime, where mu prime is an indication that we have a new coordinate system. We transform e, that goes to mu prime. And then this is going to be delta mu prime. So right now I'm just allowing everything to be transformed. But here's the stuff we know. This transforms as lambda mu prime e hat mu. Okay? This transforms as a scalar. Okay? So what we can say is, and I mean, I can write this as delta mu or delta mu prime, it doesn't really matter. If I want to take this and guess how this might transform, what I can say is, well, just making the indices work out, I would guess this is lambda mu prime mu theta hat mu. Okay? This thing is going to define this. This is just a guess. Okay? At least the indices work out because the mu gets summed, it disappears, I'm left with an upper mu prime, which is what I've got there. Here, the new indices are summed, so I'm left with a lower, oh sorry. Yeah, sorry, this should be a nu. Wow, that's loud. Okay. Oh, that was an actual human being? Yeah. Oh, sorry, go ahead.
That was me.
Oh, yeah, what'd you say?
What the hell of a sneeze?
What's the hell of a sneeze? Okay, yes. Finish up here.
No problem.
All right, folks. Okay.
Why is that me?
Okay. Boy, oh boy, oh boy. All right. So, oh, look at this. Theta mu E nu is just delta mu nu. So this is lambda mu prime mu, lambda nu prime, delta mu nu. And again, this should come out to delta mu prime, although we can erase the primes on that. So what this should be telling us is that effectively, oh, hang on. Oh, wait a minute. This delta function, which I got from this and this delta function is just going to take this and make it a mu. So let's do that. This is matrix multiplication. If I call this lambda, then this must be lambda inverse. Okay? This is just giving it a matrix interpretation. You don't have to do that. You can just keep it with all of these. But basically, if you think about it, this transformation takes me from the mu coordinates to the new prime coordinates. This one obviously takes me from the prime coordinates back to the original coordinates. So the fact that these are inverses kind of makes sense. Just trying to track what I'm doing with them. Okay? But now we've got this weird result, and I'm going to summarize this. A reminder that the basis vectors transform like this. Whereas the basis dual vectors transform like this. Okay? We're going to hang on to this. Oh, wait a minute. Hold on. If I know how this transforms, and this is invariant, I think I can figure out how that transforms. This has to transform in the opposite way that the basis, the dual basis transforms. This is the exact same story we played out with the vectors. Okay? So now I can go ahead and summarize how the components transform. And for vector components, so this is the transformation law for basis vectors and dual basis vectors. I hope you remembered everything I just said. Now we can also do the transformation of the components, and this will largely finish out the story. Okay? So as you might guess, V mu goes to V mu prime, which is lambda mu prime mu, V mu, while the components of a dual vector go to mu prime, lambda, mu, mu prime, omega, mu. This is the transformation law for components of vectors and dual vectors. I apologize, I just don't want to write out all the words.
What does the C stand for again?
That's the transformation law for components of the vectors and dual vectors. These are the components, these are the bases. Okay. Remember what I'm talking about. You've written vectors like this a gazillion times. Okay? The vx and vy are the components, that's these. And the I hat and the j hat are the basis vectors, that's these. Okay? All right? So now we've ostensibly finished up the story, but there's some more interesting connections to be made. In particular, many of you might be wondering, how the hell do I create a dual vector? I mean, I know what a vector is. Momentum's a vector. Position displacement's a vector. What the hell is a dual vector? Well, let me tell you. First of all, we can now write down the extremely gory story of a vector eating, or of a dual vector eating a vector. That is, the dual vector is omega mu, omega sub mu, theta hat mu, and the vector is v nu, e hat mu. And this is just the components times the dual basis. This is the components times the vector basis. When I write omega and v without any indices, I'm talking about the whole thing. Okay? Well, we know how this works. This gives me omega mu, v nu, the theta hat and the e hat combine to give me delta mu nu. So this I can realize as omega mu, v mu, because the delta function, which is the result of the theta eating the e, the delta function is just going to sum over this nu and replace it with a mu. Okay? But this is just going to be omega 0, v0, plus omega 1, v1, plus omega 2, v2, plus omega 3, v3. Okay? Which is going to be a number. That is, it's going to be on the real line. That should look like a dot product, right? How many of you, when you learned about the dot product first time around, they explained in terms of dual vectors? Raise your hand. That's what I thought. No, just kidding. What's your question?
How do we know it's on the real line and then the other components are imaginary?
Oh, we're gonna start out with, we're only gonna consider real component things, and so the product of real things is real. Yeah, I mean, you could extend this to a complex space, but we're not going to have to do that in this class. Maybe in quantum, yes, but not in real. Okay? So, well, let me actually dig into the details of what the dot product is. That might help us out. So the dot product, you can think of as an operation taking two vectors and giving me back a number. Okay? When you learned about the dot product, you didn't learn about dual vectors. You just said, okay, vector A dot vector B gives me a number, where there are two vectors. All right? In our language, the way this would play out is we would say, if I give you vector mu and I give you vector nu, the dot product basically gives me one of the vectors having a lowered index, and then I can sum over the index, and this gives me a number. Okay? First and foremost, it doesn't matter which one I lower. I can do that as well. Okay? So the dot product for us is taking two vectors and making one of them into a dual vector, and then you have a dual vector and a vector, and they eat each other and form a number. That's the part of the story we're familiar with. But how does the dot product take a vector and turn it into a dual vector? That is the interesting question to which I will now provide the answer. First of all, we can take a hint from Rn. So in Rn, what we know and I can do it with R2, but I'll try and do it with Rn. So if we have the components of a vector in Rn, so I'll go back to the indices ij because these just go over spatial parts, then we know how this actually comes out as a dot product. It comes out as V1 plus V2 plus dot dot dot. Okay? Everybody on board with that? This is the familiar dot product. Okay? Now what we can do is we can write this as delta ij vi bj. Because if you think about it, I and j are going to be summed over the I and j here. So we're going to get all possible combinations of I and j, but this is 0 if I is different from j, and it's 1 if I is equal to j. So that's just going to give me v11, v22, v3, as many as there are. Okay? Now, if I wanted to interpret this in this language, what I would say is that this thing is a dual vector. Which makes sense in terms of the indices, because the I gets summed over and you're left with a j. Okay? But here's the important observation. What are we using to act on the vector components to get dual vector components? Say it again? You can represent it as a matrix. What kind of matrix is it? It's the identity. It's the n-dimensional identity matrix. Does anybody know what role the n-dimensional identity matrix plays in Rn?
That would be the metric, right?
It's the metric. That's how we define the distance between points. Okay? Again, you never heard this part of the story when you first learned about the dot product, because the metric is the identity. You don't even need to write it. But what's crucial for us is once we realize what role the metric plays, we can now figure out exactly how to extend this to special relativity. So, V mu goes to V mu, or what's perhaps better, V mu, under the application of the metric, and sorry, this is special relativity, so I should use the special relativity metric eta. Under the application of eta to the components of the vector. Okay? In the special relativity case, this is not the identity. All right? This thing is, of course, the good old -1, 1, 1, 1, as long as we're using rectangular coordinates. T, X, Y, and Z. Okay? Now similarly, if I started out with the components of a dual vector, and I wanted to turn this into the components of a vector, well, it might or might not be obvious that I use the metric with its indices upper instead of lower. Just notice the indices work out. Getting the indices to work out is probably going to be 99% of your effort in this class. So get used to it. Notice, mu is summed over, so it disappears, and I'm left with an upper nu, which is exactly what I have here. Boom! That equals sign. is appropriate, okay? If this is the metric, what do you think this is? If you had to guess. Any guessers? Any takers? This is the inverse metric. I should have said it. Called it out. This is the inverse metric, but guess what? The inverse metric has the same components as the metric. Because if I take this matrix and I multiply it by itself, I get back the identity. That is not going to be true in general. It happens to be true in real space and in Minkowski space, but it will not be true in a curved space. Okay? So, the metric, or its inverse, can change vectors into dual vectors, or dual vectors into vectors. All right? And the metric is a critical part of the definition of the dot product. It was just never named when you learned the dot product. All right? Now I want to point something out to you which confuses the crap out of students, but that's okay. This expression is equal to this. Do you all understand why?
The identity with the negative 1.
So these are dual vector components and these are vector components. If I would like to change this dual vector into vector components, I apply the metric. The metric is going to be this matrix acting on omega 0, omega 1, omega 2, omega 3. It's going to form their vector-like structure, but you're going to get this minus here. Okay? So write that down and reference that when you're working homework. All right? Now I want you to notice, and this is where it gets a little confusing, here we are changing coordinates. Remember, we're going from the unprimed to the primed coordinate. That changes the mu here to a mu prime. Here, we are not changing coordinates at all. This is all unprimed. Rather, we're taking a vector and turning it into a dual vector. But this is not part of the coordinate change story. Does that make sense? Okay. Now, here's the wonderful part of this, and I think I'm missing a page. Let me just check. Yeah, I think I'm missing a page. Let me just check to make sure. Yeah, it's okay. Yeah, I have an expression where I basically, no, I guess it's right here. So this is fine. Yeah, I don't think I'm missing anything. I don't think. I'll figure it out when I get home, and I'll send you an email. Okay, so with the idea of vectors and dual vectors down, we can now up the ante, and we can turn to tensors. The good thing, though, is that tensors really are just an extension of this story that we've already seen. So let me give you some important definitions for tensors. And I'll just get as far as I can on this, and then we'll continue it next time. So tensors. One, these represent physical quantities. Okay? What I mean by that is you're used to the idea that vectors represent physical quantities. Velocity is a vector, momentum is a vector, you know. Well, tensors are going to represent physical quantities as well. They're going to represent more physical quantities than you're going to want to think about. And they are invariant. Okay, the invariance is associated with the fact that they represent physical quantities, because a physical quantity cannot change under coordinate transformation. You know, if I'm walking this way, changing coordinates does not change the direction in which I'm walking. It can change the way you describe the way I'm walking if you pick a basis and you tell my components in terms of that basis, and then you change coordinates, you change the basis. But it doesn't affect me in my physical motion. Same is true for tensors. Any tensor quantity is physical. Changing the coordinates won't change the tensor. Okay? But the components and basis will change. Okay, so it's exactly like the vector and dual vector story. Okay? 2, tensors live in flat, tangent, or cotangent spaces. Or tensor products of these at each point. Okay? Okay, I'll show you what I mean by that in just a moment. Now, in terms of labeling schemes, we have seen some tensors already. So the labeling scheme that we're going to use is basically denoting the type of tensor we're working with by a pair of integers, a and b. And essentially, the way we use this is we say 0, 0 corresponds to a scalar. 1, 0 corresponds to a vector. 0, 1 corresponds to a dual vector. Guess what, folks? You've been working with tensors since the very beginning. Scalars are tensors. Vectors are tensors. They're just the smallest, the simplest tensors. Okay? Now, you get a victim? Jared Spencer. Jared, let me ask you a question. What do you think these two numbers are telling us? I mean, they're telling us what we have, but what do you think they're counting?
Dimensionality?
Nope, the dimensionality and everything is 4. So this has got 0, 0. This has got 1, 0. This has got 0, 1. What do you think the 1 means? What do you think it's counting?
Not sure.
Any takers?
Is it the upper and lower, like indexes?
Indices, exactly. The first number is counting the number of upper indices when we write its components. The second number is counting the number of lower indices when we write its components. The scalar has no components, so that's why it's 0, 0. A vector has components v mu, upper mu. So it's a 1, 0. Dual vectors have a lower index on their components. That's why it's 0, 1. Wait a minute. This means that we know what that is. Can anybody give me an example of a 0, 2 tensor?
On the metric.
Ross, you gotta raise your hand, man. Somebody raise their hand in the back of the room. He said, "But were you about to spell that out?"
Yeah.
Yeah. That's 0, 2. What about 2, 0? The inverse metric. Okay? In general, A and B can be non-zero. So for example, you could have the tensor T, mu, nu, alpha, lambda, beta, gamma, delta, and this is a 3-4 tensor. Don't worry, we're not going to mess with a 3-4 tensor in this class. We are, however, going to mess with a 1-3 tensor. I know. Go ahead.
Where does a tensor exist if it has both upper and lower indices?
Very interesting question. Where does a tensor exist? We know that in order to have a vector on a curved space, we have to pick a tangent space in which that thing lives. So this is the tangent space. If we have a dual vector on that space, say over here, then this is the cotangent space. So what if I had a tensor that had both a vector and a dual vector index? Where would that live? Go ahead.
On the cross product or the tensor product of the two spaces.
Exactly. So it turns out that you don't need just one copy of the tangent space. You can get an infinite number of copies and infinite number of cotangent spaces, all defined at one point. So this thing would live on a cross product, a direct product actually, sorry, a direct product. That's a product like this, and this is getting into the topology of things. We're not going to have to worry about it. But basically, since this needs a tangent space and a cotangent space at each point, this is hard to draw, but that's the tangent space, and then the one I just drew is the cotangent space, and they're both defined at that one point. If I add an extra index down here, I have to do another cotangent space. So this is cotangent space 1, this is cotangent space 2. Okay? So each index needs a copy of either the tangent space or the cotangent space, all at the same point. Don't worry, we're not going to worry about that. Okay? Because it turns out, as long as you understand the story for vectors and dual vectors, the story as it plays out for higher rank tensors is very simple. Okay? So, yeah, I'm in a good spot. I'm going to be able to end this. All right. So, just if you're curious, the way that you would actually write a tensor, say it's a tensor with components T, mu, nu, alpha, lambda, beta, gamma, delta, okay? These are the components, but of course you have to multiply this by the basis vectors and dual vectors, and so this would give me E hat mu, direct product with E hat mu, direct product with E hat alpha, direct product with omega hat lambda, direct product with omega hat beta, direct product with omega hat gamma, and direct product with omega hat delta. That's the way you actually have to write down the expansion of a tensor of this signature in terms of its bases. Okay? Now here's the glorious part of this story, folks, which is I know what you wanted to hear. if I want to work with tensors and write down tensor equations, I can completely ignore this, and I can just work with the components. The basis and dual basis story completely plays out. Okay? We could include it in all of our analysis, but obviously it's a lot to write. We can get all of our expressions and our equations and everything based on just looking at the components. Now this of course means that things will transform because the components transform. Okay? But we know if we paired everything up with the basis and the dual basis, then you know we're working with invariance the entire time, which we should be because we're working with physical quantities. Now, I'm going to give you two definitions of what a tensor is, and from this, we'll very quickly write down the results and then I'll let you go. So here is a popular definition of what a tensor is. Actually, no, I'm going to give you the good definition, and then I'll give you the useful definition. I'm going to swap the order of these. So here's the technical definition of a tensor. Ready? Tensors are multi-linear maps from the space is of vectors and dual vectors into the reals. That is, if I take a tensor and I feed it a series of vectors and dual vectors, then I'll get a number. Okay? To explain what I mean by this, I'm going to give you a couple of different examples. So for example, and I'm hoping to make this a lot shorter, but if I want to feed the tensor alpha mu lambda and make a number out of it, then I obviously need to combine it with two dual vectors and one vector. Okay? So two dual vectors and one vector. This is going to give me a number. This is what I like to call a well-fed tensor. We can combine tensors with vectors and dual vectors in an underfed or starving state, in which case this will leave me with this will leave me with a vector, or we can actually overstuff it. This will leave me with a
Vector.
This will leave me with a vector. Actually, we should be careful because these are not going to be the same vectors. Okay? At any rate, so that's the definition of a tensor. You can think of a tensor as a map from the space of vectors and dual vectors into the numbers. That's the most proper definition. Here's the definition of a tensor that we are going to use throughout the entire course, and I think, go ahead.
Okay, before you do that, if we had included an extra dual vector on that last line, would the product the dual vector?
Yeah, if we had included another dual vector, this would have given us a scalar. However, I'm thinking of, yeah, if I included a dual vector with with index k, then those would be some number.
So if you didn't include the vector and you did include a dual vector, would you have a dual vector?
Yes.
Okay.
Yes. Okay. So, all right. So here is the second alternative definition, which is by far and above the one that we are going to use most often in this class, and I hope you don't laugh at it, because its use is going to be very obvious. A tensor is something, and I'm not shitting you, that transforms like a tensor.
Wait, why is this the useful definition?
I think
Excuse
that
me?
means typically don't involve
You
the
said the
word.
top one was the technical definition, and then you gave us the useful definition.
Yes,
Why is this the useful definition?
because in this class, and I want to just, this is a clue to what's coming, we're going to build a lot of things. And at the end of the day, we have to ask the question, is that a tensor? And what we do is we transform it. We do a coordinate transformation. And based on how we built the thing, we'll be able to figure out how it transforms. If it transforms according to the tensor transformation rule, which I'll start by writing down next time, then that thing is a tensor. If it doesn't, then it's not a tensor. That distinction between transforming something and finding out that it's not a tensor versus a tensor is going to play a backbone role in developing general relativity. Okay? But more on that next time.
What it looks like it does, it sounds like it does.